Ananya, can you hear me okay?
Yes.
All right. So, does anybody have any questions on anything you've looked at, read, done, OWLs, lab, anything? Okay. And now we're starting on the slide that says standard enthalpy of formation. I think it's right after that QR code thing that's useless for us. Yes?
What's the little f? Does that mean final?
Little f?
Yeah.
Well, it says it in the paragraph.
Oh, okay. I just remember in the book it didn't say,
So we start off with this because it seems kind of obscure and fairly specific or picky about what the definition is, but standard enthalpies of formation are used commonly in chemistry for doing calculations for enthalpy changes. So last time in class we saw that if we took, if we did a reaction, where's my calendar? So if you did a reaction or process, so last time we took copper and we, heated it up in water and we determined the specific heat using calorimetry. And then we used that specific heat and I heated it up really high and then put it in the water and we measured what the temperature initial was for it. How hot did we get it? So, but we can also use calorimetry to measure the enthalpy change of chemical reactions. For us, we pretty much be limited to chemical reactions that are occurring in aqueous solution. You need specialized equipment to be able to do equations or do calculations for how much enthalpy a reaction is absorbing or releasing otherwise. But the basic idea is to use those energy changes. How does the temperature change to measure those enthalpies? Now, we can also, rather than measure, calculate estimated values. So we use a thing called standard enthalpies of formation. The definition is very specific. It has you have to meet those criteria described in that paragraph to have what we would call a standard enthalpy of formation. It's going to describe an enthalpy change, a delta H, that occurs when 1 mole of compound is formed. It doesn't have to be a compound, but that's how the definition is stated. But whatever it is you're forming, 1 mole. That's why it's a subscript F. You're forming it. Okay? So it has to be a synthesis reaction. And that synthesis reaction is forming 1 mole. So the coefficient in the balanced equation must be 1. It's doing that formation from the elements that make up whatever it is you're making in their standard state. Says, how do they exist naturally at standard conditions? A lot going on here. So if you look at the periodic table over on the wall, sorry, Nanya, Can't see it on the wall. But if you look at the periodic table over on the wall, you'll see that it's color-coded by state. So all the black ones are solids. The blue ones are liquids. The green ones are gases. And it looks like at the bottom of that periodic table, it says that those are at 30 degrees Celsius. So that's not even standard conditions. Now I think the only element up there on the periodic table where that would matter would be gallium. Because I think gallium's melting point is somewhere around 23, 25. So I don't know. We don't use gallium in anything anyway. Well, at least in class. So our standard conditions are at 1 atmosphere, 25 degrees Celsius, 1 molar for solution. So if you have an aqueous solution, the ions have to be at 1 molar. The standard conditions is the degree sign. So anytime you see a symbol written with a little degree sign to the upper right, you know that that is being measured at these temperatures and pressures in molarity. It's entirely possible that you may not be given, you may need a temperature and a pressure, you may not be given it, but if you see that symbol, you know what they are. Don't get this confused with standard temperature and pressure from gas laws. Standard pressure in gas laws is 1 atmosphere, just like this is, but standard temperature in gas laws is 0 degrees Celsius. And don't ask me why. I don't know. Okay? So, degree sign, standard conditions. F, it's a formation. Questions? So as you can see in that balanced, in these equations, both of them, they both represent the enthalpy of formation for water. One of them, though, is representing the enthalpy of formation for liquid water, and the other one's the enthalpy of formation of gaseous water. It really doesn't matter what the state is for the product, it's just that the states for the reactants have to be what they are at standard conditions. Now, in the case of some compound like water, we can have gaseous water at 25 degrees Celsius. I mean, water naturally occurs at 25 degrees Celsius as a liquid, but we can have gaseous water at 25 degrees Celsius. If I were to spill water on the table, the temperature in here is never going to get above probably 21, 22 degrees Celsius, yet that's all going to evaporate. I didn't get to the boiling point. It's just going to go away. So you're going to have gaseous water because of that evaporation. When you breathe out, what do you breathe out? Carbon dioxide and water. What temperature is the carbon dioxide and water that you breathe out? What is the temperature of that? 98.5, 98.6. It's actually 98.6. I'd read an article that that's not the average anymore. It's changed slightly.
Yeah, it's like 97 point something.
Yeah. It's lowered. Yeah. Cold-blooded killers is what we're becoming. Right? Now, so we know that we can have water as a gas at that 25 degrees Celsius. So, the difference between them, the fact that we have that difference is important because it illustrates something that's really important to keep in mind throughout the rest of the year. This is not something that's going to go away. These ideas of energy changes and stuff, the reason why we're covering as first as our new material is because it's going to be used throughout. So delta H will always be positive, meaning the process is going to be endothermic. When attractions, bonds weaken or break. So if I have a chemical bond and I break that chemical bond, it is going to be an endothermic process. If I have intermolecular forces between molecules and I break or weaken those intermolecular forces, that is going to be an endothermic process. Delta H is going to be a negative value when the opposite. So when attractions and bonds strengthen, or form. Does that help a little bit?
I can't see the board anymore.
Oh, that's right. That's why it's up like that. Crap. I knew there was a reason why I was... Sorry, Nanya.
Yeah, that's fine, record.
Is it? Is it? Yeah, but there's people behind it that can't see the board now very well. Hey, is that good there?
Yeah.
Okay. Sorry. All right. Any questions?
So that one would be exothermic?
Yes. So delta H is a negative, that's going to be an exothermic process. So if we, yeah,
So what is H? Is that E?
Enthalpy.
Enthalpy? What is enthalpy?
that's a very complicated question. There's a lot going on to measure enthalpy. I'm going to make the answer short right now because the true full definition for enthalpy is way above what we need for the class. But for us, enthalpy is going to exhibit itself as changes in heat. So if we can measure the Q, the heat, that is involved during a reaction, or that the energy change in the form of heat that's involved during a reaction or a process, then we have measured the enthalpy.
So delta H and Q are like, you can switch those?
Yes.
Okay.
If you go back a couple slides, we defined delta H as being equal to Q
Okay.
if we have certain conditions met.
Okay. And so since like we always take the, like from the perspective of the, what's it called?
System.
So when there's an added enthalpy, you're adding energy into the system and breaking bonds, and then taking it out, you're, okay.
Exactly. That's what, yes. So that's why we don't even mention anymore, because we always take the point of view of the system. Okay? And if we take the point of view of the surroundings, it's so that we can eventually get to getting to the point of view of the system. So, our differences in our enthalpies of formation. When we form, so if I had a balloon, and that balloon had hydrogen gas and oxygen gas in it. Let's say I had 1 mole of hydrogen and I had 0.5 moles of oxygen. So I'm doing the enthalpy of formation. If I let this reaction take place, I spark it, I give it a little bit of energy so that the reaction can take place, and I form 1 mole of water, it's dark. Can you guys see that all right? Okay. So if I were to form 1 mole of water as a gas, as a vapor, because that's how it would form. You've seen video of the Hindenburg, right? Goes up, burns, that's hot. You're going to have gaseous water. Now keep in mind, this is measured at 25 degrees Celsius. So we would have to let the gas cool down to get the true measure of it, but it's going to be a gas. If I allow that gas then to turn into a liquid, so this is exothermic. This process right here, hydrogen reacting with oxygen producing water is exothermic, negative delta H. If I allow that gaseous water then to turn into a liquid, basically going from here to here, then I'm forming attractions. I'm strengthening the attractions or forming attractions between those molecules, meaning that that's an exothermic process. So the process of going from gaseous water to liquid water is going to release more energy. So I take hydrogen and oxygen. I react them. They produce gaseous water. Energy is released, exothermic. I allow that gaseous water to continue on to turn into a liquid. That's going to give off energy. This is why the liquid formation for water is more negative than what the formation of water is as a gas. Because we're also taking into consideration that phase change. Does anybody have any questions about that?
So you're saying taking gaseous liquid like water and turning it into liquid strengthens the bonds and it causes a loss of energy?
Correct. Correct.
Why is there a loss of energy whenever whenever bonds strengthen, why is there a loss of energy? Oh wait, okay. I know how to think of it in the reverse, like whenever you break a bond, you add energy. Why do you take away energy to strengthen a bond?
Do you remember seeing that equation
No,
when we did atomic theory?
I don't think so.
That was not the distance between the two particles.
Then maybe.
You took physics?
No.
Okay. So
Sorry, okay.
don't worry about K. K is a constant, all right?
Okay.
But the basic idea is this. V is potential energy. Okay? If D is infinitely large,
What's the
what will V be approximately?
I don't know. If D is infinite,
If D is infinitely large,
then
then V is going to be close to what value?
infinity.
0?
0.
Oh, because you're okay. Yeah, that makes sense.
Because it doesn't matter whether it's positive or negative. The larger this is, the magnitude of this gets smaller and smaller and smaller.
Yeah.
You approach 0.
Yeah.
Aren't you in calculus?
No. Don't look at me for that.
You're not in calculus?
No, I'm in pre-calc.
Oh, okay. This is your limits. Who's in calculus in here?
Us two.
Okay.
Oh, we did a
This is your
little bit.
limits and stuff, right? Your funny F's with the little 0 to infinity. Yeah. What's the matter?
We just had
We
a
had a
test
test
with
with
limits for the
limits on
first
it.
time and we all failed it
It was because she
collectively.
never explained it. She never explained
She
it.
explained it to the day of the.
Am I explaining it? Look at it, I failed. Hey, I failed calculus. I'm telling you, I did. And so, all right, now, so, but the key is up here. So, if this is infinitely far, if they're far enough apart, we essentially start off at 0. So we say that if the two particles are far enough away from each other, we're out here, all right? So we're saying at 0. A bond or an attraction is going to form because there's an attraction.
Yeah.
So somewhere along the lines, we're going to have a negative and a positive, right?
Yeah.
So if we take D from infinitely large and start to decrease it, we start moving away from 0. And if this is negative and this is positive, this is going to be a negative value, right? Now, negative value, but the magnitude getting larger. Do you understand the difference between you understand what magnitude is?
Can you explain it? How?
Magnitude is just, think of it as the absolute value.
Oh, okay. So it's.
It's getting closer to negative infinity.
Correct. So if they get closer, what happens is our value for V, because this is a negative and a positive, this has to be a negative value. So as they approach each other, since our energy is decreasing, energy has to be released. That's why it's the negative value.
Yeah, that makes more sense.
Okay. Now, by definition, elements in their standard state, that's important, are defined as having an enthalpy of formation of 0 because they're already here. You don't have to make the elements, they're already there. That's why they're defined as 0.
I'm still confused on why water would go to a gas before a liquid.
Because the reaction is occurring at a high temperature. So if I started off with hydrogen and oxygen gas at room temperature and I gave it a spark, that temperature can shoot up. It's going to well above 100 degrees Celsius. So the gas that's going to be produced is going to be in the vapor form. Now if we let it cool down and the container's big enough, it'll stay a liquid. That's why, so who's got a water bottle? Irving, hold your water bottle up. Oh, it's not, your water bottle, hold it up. So in that water bottle, if it's like got, a third of the way full, you cap it up good and tight, the water's going to evaporate, but it'll stop because you saturate the air with the amount of water it can hold. It's kind of like 100% humidity. Okay?
So like solubility.
You can put it
before
down
the
there.
air.
What's that?
So it's like solubility before the air.
Kinda. So if the container's large enough, so if I took, if Irving's bottle had it was third full with water, and I poured it out on the ground in here, it's going to evaporate. It's not going to stay a liquid because there's enough room or space in the air for all of the water molecules to stay a gas.
So is it kind of like, I don't know if you remember last year I asked you about the fridge and about why there's water vapor in there? Is it kind of like that?
Mm-hmm. Second semester we'll look at a thing called entropy, and that helps explain it as well. Okay. Now, okay, so let's look at an example of how this could be used. So enthalpies of formation are useful when you would like to know how much of an energy change a reaction or process is going to have without actually doing the reaction or process. Now,
What was that?
Now, Dylan,
Yes,
you have a book sitting in front of you, right?
I have an iPad.
You have a book sitting. Where's the?
That's in front of you, Dylan.
Oh, yes.
Did you put that there?
Yes.
It's supposed to be at your desk.
Okay. Well, it was in the center of my desk.
I know.
Are those
It's
all
what
your
it.
pens? Are those all your pens?
These
Color
are mine.
code
I have
just
to, I can't put them on top of my pens.
All right, Emily, you're gonna take over.
That would be a tragedy.
I mean, they're in perfect order. No, that's
Write
not
this
mine.
equation down.
They're rainbow.
Okay. So, if I wanted to know what the enthalpy of that reaction is, we'd either have to actually do the experiment or we can go look crap up. And since we don't have the equipment to do this reaction in the lab, we go look it up. Emily, since you now are in control of the book, the index card at the furthest back of the book. You have a table of thermodynamic data, correct? Okay. So, in that table, they give us the enthalpies of formation. They do not write out the reaction, though. And they don't need to. Because every one of those reactions, the product is what it is that we're interested in. And the product was formed from what? The elements as your reactants. So we don't need to know what the whole balanced equation is because we know it's just going to be the reactants at the beginning. Now, under the carbons, find C2H6. What is the value in the first column of numbers? Because those are the only ones we will use.
Negative 84.7.
Okay, so now that's the value. What that means is that's how much energy would be released when 1 mole of ethane was produced from its elements at standard conditions. I know it's a lot to say, but it'd be 2 carbons, 3 hydrogens, H2s, giving you C2H6. That would be the reaction. Kilojoules per mole because it's 1 mole of that compound. Yes?
Can you say that one more time? What is it again? It's how much energy is released with what?
This is how much energy when 2 moles of carbon
Okay.
and 3 moles of H2
Okay.
react to form C2H6.
Okay.
Well, I said in the table they're not going to tell you they're not going to give you the reactants because they're all of them are just the elements. And the coefficients on them would have to be the coefficients to make 1 mole of this.
I thought those would be the reactions, not the products. Why are we looking through from the left side of the equation?
We're not there yet. Wait a minute, Cameron, you had, yeah,
Yeah, did you say 6 moles of hydrogen?
3 moles of
3
hydrogen,
moles? Why would only 3?
3 H2s.
Oh, okay. Duh.
So then would it be 0 for the O2?
Exactly, good, because that's the next one I was gonna go to, and I was gonna see if anybody could know it right off the top of their heads. JT,
How is it 0?
what's the standard state of oxygen?
0.
And that's its element. So elements in their standard state, their enthalpy of formation is defined as 0. All right, what's the enthalpy of formation for carbon dioxide?
Negative 393.5.
And for gaseous water, you got to be specific because you're going to have both of them right next to each other. It should be in the hydrogen section. Turn the page.
That's just the C's.
Negative 242.
42?
Yeah.
Even?
Yes.
Matul?
Wouldn't you need energy for O2 since it's O2? Because there's 2 oxygens, so there would be a bond.
Because oxygen is naturally found as O2.
I thought it turned into O2 because there was O's nearby, and then diatomically 2.
So what we're doing is we're kind of laying we're saying that oxygen's value is 0 as O2. If I had oxygen atoms, so separate oxygen atoms, that would not be a 0 value in our enthalpies of formation.
What would that be?
I don't know. It would have to be positive though, because you would be taking an O2 and breaking it apart. Does that make sense?
Yeah.
So that's why the definition is very specific. The elements in their standard state are defined as 0. Okay? All right. Now, the reason why we looked each one of these up is because we can determine how much energy is absorbed or released but from this reaction, from this data. Okay. Now, our enthalpy of reaction, notice I don't have a little f on here.
What's the little f mean again?
What's that?
What's the little f mean again?
Formation.
So what's the difference between, like...
What's that?
Like,
What's
so,
the
like,
difference?
What's the difference between with and without f?
So, this is not a formation reaction, right? Can't be. It violates all the rules for us to have a formation reaction.
Just a quick reminder, what a formation reaction is.
Enthalpy of change that occurs when the one mole of compound is formed from its elements. So the elements have to be the reactants. You can only form one compound, one mole of compound.
And it can only be elements in the reaction?
Exactly.
Okay.
So because those are compounds and that's 4 moles of carbon dioxide, it doesn't work?
So if it was like
Correct.
carbon and oxygen to carbon dioxide, it would be a formation?
If you were forming only one carbon dioxide. Plus, we have 2 products. You can't have 2 products. So your formation reactions are always for a single compound, 1 mole of it.
So what's the difference between how you find the enthalpy of a non-formation versus formation?
The enthalpy of formation for a reaction that's not a formation, you have to calculate. The enthalpy values for enthalpies of formation, they're in lookup tables.
Oh, okay.
That's why Emily's got the book.
Okay. Okay.
Who's done the owls in part 3? I was just saying, you guys know, you might want to get on that. Yeah.
So it doesn't matter how many moles you need of the elements, as long as only one mole of the compound is made?
Exactly.
Okay, so like sodium chloride to make sodium chloride would be an example of,
So sodium plus chlorine giving us sodium chloride. When we balance this, we would need a half mole of that. So yeah, that's why in these it's got a half mole for the oxygen. So for enthalpies of formation reactions, you're going to have to use fractional coefficients at times to get that to happen.
So like, if there's only supposed to be 1 mole, why are there 4 moles of carbon dioxide and 6 moles of water?
Okay, so I'm setting this up to look at something here in just a second. So this is not a formation reaction, right?
Why isn't it a formation reaction? Oh, because it's a combustion reaction? No.
You're forming more than one product. So in a formation reaction, again, you're only forming one product. You're forming 1 mole of that product,
Okay.
and the reactants have to be elements.
Okay.
If you don't meet any one of those criteria, then it's not a formation reaction.
And then it doesn't need to be like 1 mole of each?
Correct.
Okay.
But we can use that information to find out how much energy the reaction. So we can use the enthalpy of formation information to figure out how much energy a reaction overall
Okay.
is either going to absorb or produce.
So because we know the formation energy, enthalpy of all the separate compounds, because they form from formation reactions, we know how much energy was exchanged from one end of the reaction to the other.
Yes.
Okay, that makes sense. So the formation reactions are just used to help with the more complicated reactions. Okay.
Okay, I don't want to spend a whole lot of time on this one, so I just switched slides and on you. So in number 6.45 up there says, which of the following standard enthalpies of formation values is not 0? So I'm just going to go through it quick. Sodium, solid, 0 or not?
Why would it be 0?
So sodium solid, what's sodium's natural state? So 0 or not?
0.
Neon gas. Up here too.
Wait, why is it 0 if it's in its natural state?
It's 0.
Because that's the definition of a standard or a standard enthalpy of formation for an element.
Oh, so like the way that the oxygen is 0. Okay, okay.
That.
Sorry. Yeah, okay.
Neon, gas, 0 or not?
0.
Who said not?
Oh,
Who said
is
not?
it not?
Who said not?
Is it not?
I heard somebody said not.
Not.
Was it you? Cameron.
Is it not?
It's 0.
But isn't it a diatomic?
No, not neon.
Isn't that what that green means?
Gas.
Green means gas.
It's a noble gas. It doesn't.
Who'd you have for chemistry?
It's 0.
He had Milligan with me.
Mr. or Mrs.?
Mr.
Didn't he sing you your song?
Yeah.
The Magnificent.
The Magnificent Seven?
Sing it
Played the
again.
music.
Na 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 na.
He was on
didn't
his
sing
phone
that?
at the time.
I don't
It was 3 years ago. Sing it again.
Oh, come on, you can't forget Milligan singing that song.
Sing it again, maybe I'll remember.
No, I don't. I can't do it like he can. I'm not going to even try to replicate. CH4 gas.
They must have
0 or not?
Not.
Not. Because?
It's not.
Not an element. Okay, I'm going to go ahead and just tell you this is 0.
Why?
Because
It's still
sulfur exists. So you know how you guys know the diatomics? Okay, sulfur is kind of like that. It exists as S8 molecules. So that's its natural state.
That's creepy.
Is it?
If you run across that, just keep that, it's just one of those things filed away so you're not overly confused when you see it. Mercury is a liquid. 0 or not?
Zero.
0, because mercury is a liquid. H, gas. 0 or not?
Not, it's not atomic.
It's not 0 because it's not H2.
Oh.
Why,
Okay, gotta be careful.
wait,
Wait,
so it is not,
it is not 0. If it was H2, it would be 0.
We should plan
Okay? All right, I'm going to skip that second problem because we want to get. So Hess's law. I was a very bad teacher. When I made these slides, I put a plus sign in there. That should be a negative. That should be subtract. I know. I know.
I'll listen to after.
okay.
Ernie said it's not.
So our
If you're in the
enthalpy,
slide, it's supposed to be on.
our enthalpy of the reaction, the enthalpy change for reaction, will equal the enthalpy of the change of our products minus the enthalpy of formation for our reactants. Now this relies on what's called Hess's law. Hess's law states that it doesn't matter how you carry out a reaction. The energy change going from your reactants to your products will always be the same. So did I ask you guys about how you got from your previous class to here last time?
Yes.
Okay, 2 times ago. So if that basic idea, sorry. Now, I'm going to try to speed this up a little bit from what I did in the previous period. So 0, 1, 2, 3, 4, 5, 6. Okay, I'm going to start here. I'm going to have 4 steps. So my y-axis represents the enthalpy, not the enthalpy change, the actual enthalpy. So if I was able to measure what the actual value of the enthalpy is, this would be it. This is the progress. So this is going to be a reaction that occurs in 4 steps. So my first step, we'll start off with you, Dylan. I'm at enthalpy of 3. What enthalpy do you want to go to besides, you can go up or down for the first step?
Let's go to 5.
So my first step, my enthalpy change in my first step is going to be +2. Yes.
So, if you said that enthalpy is basically the same thing as heat, and you can't measure heat at an instant,
Enthalpy changes.
enthalpy
Let me clarify that. So when we talk about the heat, that's going to be a change in the energy. That's our change in enthalpy. We can't know what the enthalpy started at. We can't know what it ended at, but we can know the change.
So this is.
So
that's
my
theoretical, you
yeah.
think
So
actually
my
that's
my
not
little
real.
points here. That's hypothetically if we were able to say
Okay.
what is the enthalpy,
But we can't.
but we can't know that.
Okay.
Okay. So in my pretend little universe, I can know everything. All right.
Was Obi-Wan better than Anakin?
What's that?
Was Obi-Wan better than
Canon or non?
Ooh.
Canon.
I don't know. Obi-Wan better than yeah.
What
Obi-Wan.
about non-canon?
Still.
Oh, Darth Maul. Man, he was awesome. Come on. So, second step, we go from an enthalpy of 5 to Andrew.
2.
So we have an enthalpy change in our second step equal to -3. You all right?
Yes, sir.
Analia,
Oh,
where do you want to go next? Third step.
let's go to 0.
Okay. So our enthalpy change is equal to -2, 3. No, 2, yeah. We were at 2.
Simple math.
Yes, simple math.
In my universe.
In my universe, it may not be. So, last step, we go from 0
To 6.
6.
Yep.
So, what Hess's law says is that the enthalpy change for overall, for the process, no matter what the steps we take are, is going to be the sum of all the enthalpy changes of the individual steps. So our first step was a +2. Our second step was a -3. Our third step was a -2. And our fourth step was a +6. So the overall enthalpy change for this reaction is +3. Because we're starting here and going there. That's the overall enthalpy change. So Hess's law is telling us we don't need to know all of the individual steps. Their sum is going to be the same no matter what. So as long as if we did this again, but we said it has to be this process, whatever that is, we could have whatever we want in terms of our changes, but if we would have to have started at 3 and ended at 6.
Bless you.
So where does the product and reactant come in? Like, is that?
Hold that thought.
So it's like displacement, like change in displacement?
Exactly. So in physics, this is the displacement without the work. Because the work would be all the distances, right? So the total amount of work would be how far you had to move whatever it was. This is just simply, you're right, the displacement. Okay? All right. Now, how does that relate to these numbers? Well, remember we said Hess's law says it doesn't matter how the process takes place. All that matters is you got what you start with, you got what you end with. Here's what we're starting with. These are our reactants. Here's what we're ending with. These are our products. How we get from there to here doesn't matter. So let's think of it this way. If I were to take this reaction here, this compound, this is the formation of it, right? But if I were to run it backwards, take it apart into its elements, that would be positive 84.7 for each one, correct? And I would have the elements. This is an element already. Don't need to do anything to it. I could then take those elements that I got from taking apart the ethane and my oxygen and put together these, which would be a formation, right? How much energy is this going to release? But this value here is going to be a negative value because we're forming it. This is going to be a negative value because we're forming that. And these are formations. This sign changes because we're taking it apart, not putting it together. So we have, for ethane, if it releases 84.7 kilojoules per mole in the formation of it, but we're using it as a reactant, meaning we have to take it apart so we can use the pieces, then we're flipping that sign And that's why this equation is set up the way it is.
So if instead of oxygen it was another compound with two different things, they would both be positive? If like they were switching?
Or whatever whatever sign it had to be.
Yeah.
Remember, enthalpies of formation, most of them, so Emily, you can confirm this, most of those enthalpies of formation are negative values. There's a positive one that shows up every once in a while, right?
Yeah.
But most of them, by far, most of them are exothermic processes. So, our equation is set up the way it is because these are being formed. How much energy is absorbed or more than likely released in their formation, we don't want to change that. So we would have negative 393.5 times 4. Why? Because that's the amount of energy that's released for each mole of carbon dioxide, and we've got 4 moles of it. Everybody okay with that? Plus, negative 242 times 6. Because that's how much energy is released when water is formed. We're forming it here. Close my bracket. I'm done with my products.
Wow, thank you. Feel special.
That was really nice.
Now,
Jeez.
everybody good?
Yeah.
Now, we flip the sign. So the reason why this is set up the way it is, we want these normal. We need to flip the sign for our reactants. You think of it like this. With the exception of one thing that we'll probably have time to see today, all of our equations are final minus initial, right? Products are final. Reactants are initial. So we're doing the final minus initial thing. Minus negative 84.7 times 2. Now, in my explanation up here before, I said we're essentially taking this apart, which means we need to make this a positive, right? Don't change the sign when you put in here, though. Use it as is. The math and the setup of the equation is doing that for us. Because the quantity that we have over here has this negative sign on it. Everybody okay with that? Times 0 times 7. I put that just to emphasize the fact that you want all of your reactants, all your products represented. In practice, would you do this? Nah, just leave it out.
So with the graph you did before, you just added everything together to get the change. So why can't you add everything together to get the change with this?
So in this case, it's not, in this case, you say it's essentially one step. We're going from here to here. If you thought of it as multiple steps, okay, we've got to run this backwards. Then our next step would be, okay, let's make our carbon dioxide. And then our last step would be, let's make our water. And then we add those together.
Okay. So
This is a way of doing that, if you wish. Just a second.
Why is the negative sign on the outside of the thing for the reactants? Is that because it's minus, so then whatever you get, you just add them together for both? Like whatever you get for the products, you add to that because it's negative now?
In a sense, what this is essentially doing is flipping the sign of everything in here.
So then when you plug it into that, you just add them together instead of subtracting them? Or
How,
just-
what, you do this math.
Oh, that's it, okay.
That's the equation.
Oh, you just didn't have space, so you put it underneath.
Oh, yeah, I didn't.
Okay, I thought that those were two
Oh,
separate
no, no,
things,
no,
and
no.
then you were gonna
I-
get done and like add them, and I was like, why didn't you just subtract? Okay, that makes sense. Sorry.
Is there supposed to be a plus in between the parentheses? Okay, alright, I was just making sure, I was
Is that
like,
what
wait,
you're-
0.
Thank you. What was the rule I made last time?
Oh, no times?
No?
Oh.
No.
No,
I don't
what?
know.
Oh, did I not tell you my new rule?
No.
When I start writing numbers on the board, you start getting calculators out and punching the damn button.
I've got
Let's
your
go.
answer. Negative. I already have it. I'm way ahead of you.
Good.
So it was the exact opposite of no calculators.
Yeah, exactly.
No calculator.
Negative 2. How many single things do you want?
Just keep it to the ones place.
Negative 2,856.6. So then I guess that'd be 7. There you go.
Now, somebody else do it to confirm or deny that.
I can use
I
the
always-
calculator.
Yeah, everybody can use the calculator, but using it properly every time, even I don't do that.
I got a different answer.
Anybody
Don't
else get a different
listen to
answer?
him.
I'm gonna do it again just to make sure it's not
The answer's no.
stupid.
Yeah, Cameron. Emily got the same number.
So can somebody confirm 2,857?
I'm trying.
No, wait.
You can?
I didn't get this.
Is Mitchell backing me up?
Is that a go-go squeeze?
Yes, it is. I didn't wait until I finish my lunch.
I see from where I sit in Mrs. Elder's, I
I
see
got
a
that.
stash of them in the
I can
cabinet. Like I can see right through the door
Yep.
to the box.
I got a different number.
I got the same number.
Yeah, I got
the
it.
same also.
Okay.
Okay. Yeah, me too. Back off.
Actually, oh yes, because he rounded, yes.
We good?
Yeah. Well, so you get a different number if you put like 2 parentheses for the last number instead of just 1.
That's what I did.
Yeah, that's what I did the first time, and I got like 100 more. Or negative 100 more.
They didn't do the parentheses right.
Like if you do 2 parentheses, if you do negative parentheses, parentheses, negative 42.7 times 2, parentheses, parentheses, you get a different number.
47.
So you
I mean, negative 4.7.
I'm right.
Okay.
Dylan for all he needs to do.
So basically, so this is why we can use the table of thermodynamic data. You're going to have to do this in your owls. I would strongly encourage you when you're doing your owls to do it through Safari or Chrome or whatever your favorite browser is. I'm pretty sure Chrome works a little better than Safari. That way you can open up the thermodynamic data and have it in its own tab, and you don't have to go back and open it up. If you go through the app to do these things, that's more of a pain than anything else.
Would they also be in the book?
When in owls, do as the owls. So the numbers that are in the book and the numbers that are in the owls may be different. We've run into that. It depends on the data set that they're using.
How do you find it in the owls? References?
Yeah, it's going to be references. And it'll say thermodynamic data. Okay. So this equation is useful because if you don't know what the energy change is going to be, you can predict what that energy change is going to be by looking up the thermodynamic data for the reaction you want to do and calculate it out. Is it going to be perfect? Probably not. I mean, there's other factors to take into consideration, but it's going to give you a rough idea. Use this in industry and in research all the time. If they want to carry out a reaction, they need to know, is this reaction going to be exothermic or endothermic? How much so? Are we going to need to take safety precautions? Okay?
I think we explained this last time, but why would there be a different number? Like, what would cause that to be higher or lower? I think we...
Just They should be the same.
Okay. But if you do get it different, would it be because of like your equipment? Or
Yeah. There's always gonna be some error in the equipment, in the measurements. There's always some variation in that. That's why we use our significant digits.
But the elements themselves will always
We define those as 0.
that much. Okay. Or will change that much. I'm not understanding.
They're not going to change significantly. You're not going to find one data table is going to be 100 kilojoules different than another. Maybe 10. The other thing is, it also depends on the chemical bonds themselves. You know, what's bond? How is the molecule arranged? Most of the time, so our thermodynamic data tables they're relatively, the compounds are relatively simple. They're ionic compounds most of the time. But when you get more complex, larger molecules, there can be some variation in there because you wouldn't be able to predict it exactly until you actually did the experiment. Okay? All right. Questions on that? So, let's apply. So, Emily. So next slide, 6.51. Emily, what is the enthalpy of formation for calcium carbonate?
Negative 1,207.
Calcium oxide?
Negative 635.
635?
Yes.
And carbon dioxide?
Negative 393.5.
So, for that equation, find the enthalpy of reaction using the enthalpies of formation given to you on the board. You didn't have to do any multiplication, so it's just addition and subtraction. You got an answer?
I do have the answer. Would you like the answer?
I would.
Okay. Positive 178.5.
I second that.
I third.
I got what Dylan got.
Okay.
Hold
I'm
Questions?
gonna roll with this today.
This is.
on. Is that
Is this all we're learning?
exothermic?
Huh?
The reaction, is it exothermic because it's positive?
Endothermic.
Endo, I thought endothermic had to be negative.
Because
Never.
it's receiving energy.
Oh, I see. Oh, never mind then.
Endothermic.
That's right, yeah. I think I was getting I meant to say one. Yeah.
Is this the only new concept we're learning today?
Nah.
Okay, good.
Why, is it too simple?
No, I'm very excited that I understand one.
I'm excited that you're excited that you understand what's going on.
I would like to
know who know wacky
Okay, 6.52. So we can use the enthalpy of formation data, not just to find the enthalpy of a reaction, but to we could use it to find the enthalpy of formation for something we don't know the enthalpy of formation for.
Whoa.
And that's how basically that table, when you go to lookup tables, that's basically how it was done. You start getting a library of reference, and you start using that library of reference to get new ones. Because again, Hess's law says it doesn't matter how you do the reaction, what you start with and what you end with, that's all that matters. The enthalpy change is going to be what was the enthalpy before, what was the enthalpy after. The change doesn't matter what the pathway is. So, we have that reaction. The only other piece of information that we need is for the HCl. So what is the, Emily, what is the enthalpy of formation for HCl? It's in the hydrogen section. No, it's in the chlorine section, I'm sorry. I think.
Negative 92.
All right, so negative 92 kilojoules per mole. That's the enthalpy of formation for the hydrogen chloride. We know the enthalpy of the reaction is negative 74.9. We don't know the enthalpy of formation for the chloride ion. That's what we're looking for. They tell us in the question that the delta H, the enthalpy of formation for the hydrogen ion, is defined as 0. Solve. What is the enthalpy of formation for chlorine? Can somebody tell me how to set it up? Dylan?
So would you go negative 74.9 is equal to the sum of your products? So what would be the chloride, whatever that number would be?
You don't know. That's what you're finding.
Yeah. Do you want me to keep going?
Well, yeah, that's your unknown, right?
Yeah. So then plus. Don't you want to? Okay. Plus 92. Well, don't you want to close that off first and then do the minus negative 92?
What's my other product?
Zero. Or okay. So then go minus the negative 92.
Yes. JT.
What's that symbol you put, like, is it just, like, I just put CL minus, like,
That's fine. I'm being specific about it. You could call it X for all I care. I don't.
All right.
Doesn't matter.
Why is it so big?
What is it?
Very big, and it makes me uncomfortable.
What do you have?
Negative 166.9.
Looks pretty small to me.
Oh, that's what I meant. I was talking about magnitude.
Okay, there we go. Good. Actually, good question. What is the standard state for chlorine?
CO2.
Okay, so to get from Cl2 to Cl minus, you have to take a chlorine molecule and break it apart. Okay, that's an input of energy.
So do you have to input that much energy?
No, not exactly. Because now you broke it apart, now you have a chlorine atom. And a chlorine atom is neutral. Now you got to add an electron.
Oh.
So you got to make it negative. Now that's a little complicated because you've got attractions and repulsions going on there because you've got an atom that's neutral and you're trying to put an electron in there that it doesn't necessarily want in the first place.
Yeah.
Okay. Then it's not just chloride ion, it's chloride aqueous. So what is the interaction between the water molecules and stuff? So it's not as simple as what you might think.
So we wouldn't have been able to find it without the negative 74.9 and all that.
Exactly. So what they're telling you is that if you took hydrogen chloride gas and you dissolved it in water, if we define H plus aqueous as being 0, then that's what it has to be based on our Hess's law.
Why is the H plus 0?
Because it was arbitrarily defined as 0.
You can do that.
Okay. But if the chlorine
They could have just as easily defined it as negative 1 million.
So in reality, the answer isn't negative 166.9. That's just for the purpose of
In this,
this question.
So if we were to actually do that, the H plus wouldn't be 0?
Would there be any way to find the actual H plus?
well, they've defined it as 0. Why would you go find it if they have defined it as 0?
Because I'm very curious.
Actually, so when you're dealing with aqueous solutions, things get complicated. And that's why they've kind of taken the easy way out and said, we're going to define this as 0. So ions, usually we don't mix and match too much with the states, with the aqueous stuff. They're included in the data table. I mean, if you go through and you look at the data, you're going to see those ions. It would make more sense to have things in similar states than to be going from gas to aqueous. But we can find those values. If I took hydrogen gas and I dissolved it in water, there's going to be an energy change. And in this case, negative 74.9 kilojoules per mole. Now, what the actual value is for the chloride, I don't know. We've defined hydrogen H plus as being 0, so based on our calculations, that's what it's going to be. And because we defined hydrogen gas as 0, and most of the other ions are compared to it, they're valid values. Okay. Other questions? All right. I'm going to skip that one. Skip B and go to 6.62. So Nanya, I skipped a slide there. 6.62. Okay, so Hess's law, there's several different, I guess you could say, flavors or approaches with Hess's law. We've just used the enthalpy of reaction, using the enthalpy of formation for reactants and products. Another way is using the system of equations. So if we know these three reactions and we know what their enthalpies of the reaction are, we can find other reactions based on that.
Are those all formation reactions?
Technically, yes,
Except for that last one?
except for that last one. Okay?
Why do you say technically?
Because if you look at the first one,
Yeah. Graphite?
graphite, that's the standard state for carbon.
Mm-hmm.
Because carbon has several. Diamond's one of them, graphite, Buckminster fullerenes, there's a whole class of carbon molecules, if you wish. But graphite's the one that is standard. Diamond is not, because there's a slight energy change to go from graphite to diamond. I say slight, it's not easy, but it's a slight energy change. So if you look by definition, I have 1 mole of carbon dioxide being produced from its elements at standard state. And it's got the degree sign. Same thing here. Our water, we got 1 mole of liquid water being produced from the hydrogen and oxygen gas, standard. So they could have put that little F on there rather than just reaction. But the last one is not, because you're not forming just one product. You don't have elements as your reactants, blah, 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 okay? But we can use those 3. So this is the equation we want to make. I'm going to abbreviate graphite as just GR.
This seems crazy to me. It's like systems of
So this is what?
It's like systems of equations in algebra, and I don't like it.
Oh, this is easy systems of equations.
Okay, good.
So this is the equation we want. These are the equations that we have to make this. So the way I do it very systematically. You know, what do we have? What do we need? What do we got to change? So I need graphite as a reactant. In our first equation, we have graphite as a reactant. So we're going to use that equation. We're going to have graphite plus oxygen gas giving us carbon dioxide gas. The enthalpy change for that is 393.5. There's only one problem. in our final balanced chemical equation, how many graphites do we need? We need 2. So I don't need 1 of this, I need 2 of this. So I'm going to double everything. This reaction has to occur 2 times to accomplish what we need. Remember, enthalpy is an extensive property, meaning it depends on the amount of material. So if I have this reaction occurring 2 times, then I need to double this value. Whatever you do to the chemical equation, you have to do to the enthalpies. All right. I need hydrogen gas. There's no hydrogen gas, so we need another equation. That's our second one. So hydrogen gas reacting with half a mole of oxygen gas. I don't like fractions. Oh, liquid. Negative 285.8. How many hydrogens does the reaction need? I need 3. So I'm going to multiply everything in my equation by 3. And I do the same to the energy value.
What did you multiply it by 6?
Why?
I got the wrong. No. I was confused. Hydrogen and oxygen.
You were to 2.
Oh. So I took care of my graphite, took care of my hydrogen, now I need ethane. Ethane's in the 3rd equation, but what's wrong?
It's not a formation.
Doesn't matter. That doesn't have to be a formation. It's not the same amount of moles, but none of them have been up to this point. We can fix that.
It's a reactant.
It's a reactant. We need it as a what? So we got to write that reaction backwards. So we're going to have 4 carbon dioxides. We're going to have 6 water as a liquid. Carbon dioxide is gas. It's going to produce ethane, C2H6, but 2 of them, and 7 O2s. That reaction, now we would report the value for the enthalpy as what? Positive, because it's negative as it was written. But now it's positive 3,119.6. And we got a problem still.
Divide everything by 2.
Divide everything by 2. So that gives us our 2 carbon dioxides, our 3 waters, 1 ethane, and 3.5 oxygens. How do I know this is right now? Oh, and we've got to divide this by 2. Because if we go through and we combine these 3 equations, just like what we did with the redox reactions. Remember when we took the 2 half reactions and we brought them together? And we cancel out the stuff that's the same on both sides. We combine the same thing on the same side. I need 2 graphites. I don't need to do anything to it. I need 3 hydrogens. I got those. And I need 1 ethane. So the things I have circled, I don't want to do a thing to. All of the other things need to disappear. two CO2s as products will cancel out with the two CO2s as reactants. Three waters as products will cancel out with the three waters as reactants.
Oh no, that's sick.
We have three and a half oxygens as products. We have two oxygens here, 1.5 oxygens here. So we have a total of 3.5, and 3.5 they go away. Everybody okay? Tool?
What if things didn't cancel out?
Then you've done something wrong. So you're going to be given enough information for you to be able to write the reactions out to get everything to cancel except for what you need. You just need to make sure that, remember, you can flip reactions and you can multiply or divide them. Whatever you do to the reaction, you have to do to the enthalpy.
So then how do you find the enthalpy from there?
Add these up.
Add all of them now?
Dylan?
So they're always going to cancel the things you don't need. So then can I just not do all of that and multiply the enthalpies by the number that I need to and then just add them?
Yeah. I mean, if you don't want to write it all out and you know it's going to happen, because the ones that are given in these problems, and even on the AP exam and my exam, they aren't going to be that challenging. I think the most I've ever seen is maybe 4 equations that need to be added up. I mean, it could get more complicated, but
So you can just like take the enthalpy of every reaction and change it depending on how many moles you need and add them all together?
and revert. You know, if you needed to reverse, make sure you change the sign. Yes. Done.
So wait, wouldn't you take the top two and add them and then subtract the bottom one from it? Because if the bottom, or take the bottom one and take the top two and subtract the top two from the bottom one, because the bottom one is the bottom.
But they're not products or reactants. You're looking at it as the whole reaction. That's where the system of equations part comes in. You're looking at, so we're looking at, so think of it, Hess's law says it doesn't matter how you have the reaction take place, right? So I have a reaction. So let's say this is one step. I make carbon dioxide. And then I have, this is another step. I get water. And then I take those two and I make this as my third step. Okay? That's one way of thinking of it. You can think of it as, many different ways. But in the end, here's the thing. It doesn't matter. This reaction rearranged to give us this. That reaction rearranged to give us this. That reaction rearranged to give us this. The sum of them would give us that enthalpy.
Okay.
So I wouldn't necessarily think of it as that this is reactants and this is products. You're going to have this minus those, because it may be more complicated than that.
Well, so if those values are for the entire reaction, wouldn't you need to take out the enthalpies for the things you canceled?
Nope. Because they're required to complete those steps.
Okay.
So what we're saying is, in total, all of these things are required to make this.
Okay. I see.
This is this is kind of the net. So if we said all of these things are required for this to take place, but in chemistry, we only deal with what do we start with, what do we end with.
Okay.
We really don't care right now anyway. We really don't care about what's the step in between.
Okay.
All right. What's the answer on this?
Negative 7,801.2.
Negative 84.6.
Yeah, I got that.
Yeah.
I think I'm using Dylan's calculator.
I think you need a second calculator over there.
I think I borrowed it from Dylan.
Okay, so I wanted to get to bond enthalpies, but that's okay. Let me give you a quick, just a quick overview, because if you start in on your in the owls and you start looking at some of the bond enthalpy values. The thing about bond enthalpies is you need to know the Lewis structure. I will on the test I will give you the Lewis structures. So that's my Lewis structure for a hydrogen, right?
Yeah.
That bond has a certain amount of energy associated with it, correct?
Yes.
Oxygen, same thing. I only got one of those. I got 2 waters. So you would have a table that tells you how much energy does that have? How much energy does this have? How much energy does that have? And what you would need to do is you could go through and say, how much, we're breaking that. That would be what? Positive or negative? So we're breaking those, multiplying by 2. Breaking that, multiplied by 1. Forming 4 times OH.
Negative on that side.
I don't even know how that happened.
Okay? In your notes, if you go to look at your notes for reference, I did the same thing again. This says positive in your notes, it should be negative.
I'm gonna take a picture of that.
And don't ignore my spelling of product.
Thank you,
Hey, thanks. You guys have a good weekend as well.
Have a good weekend, Mr. Okay. Bye, Nanya.
Bye. Not, it's,
Bye, Nadia. Have a nice weekend, Mr.
bye. Thank you. Where are you at? Bye.